This presentation is about X-ray tomography investigation of defects on niobium coated copper radio frequency cavity. First, I want to tell you a bit about what is cavity doing in synchrotron. Yeah, thank you. You can see here a particle bunch enters in the cavity and electric field applied to this one, and the particle is accelerated in the direction of the beam. But the problem is during this, when the radio frequency applies to the particle, the heat appear, and this one makes the performance of cavity goes down. That's why the scientists suggested that we use a superconducting thin film in this kind of cavity. Here is the Tesla-shaped cavity that is using in CERN. And what is the definition of a good cavity? A good cavity, we measure the performance of the cavity with quality factor, and the quality factor should be more than 10 to 10. And what is the main problem of the cavity is the field emission. Field emission appears when any debris or any particle appear in the cavity. Also, when radio frequency field applies on the electron, it can be released from surface of the surface and accelerated. This released electron will impact on the cavity wall and creating X-ray and again reduce the quality factor of the cavities. This is a particle that we found in this cavity that makes heat zones and decrease the performance of the cavity, because this cavity, when this particle appears in the cavity, the quench cause and the superconductivity lose their behavior. You can see here it's a kind of deformation in the surface or defect in the surface. What you can see here is a niobium coating that is a helium for cooling the niobium, and is the critical temperature of the niobium. But when the defect appears, the current goes around this defect and increase the temperature. That's why you can see here that then the performance of the superconducting coating affect but this deformation. That is why it's very important that the surface of the cavity would be without any defects. Here is the superconducting type 1. We have two different types of superconducting, type 1 and type 2. Here is non-superconducting metal that the resistivity is not 0. But you can see here that in superconducting type 1, like mercury and Pb or zircon and Zn, when the temperature is more than critical temperature of superconducting, the electromagnetic field can pass through the superconducting. It means that the temperature when increase more than critical temperature, the superconducting type 1 lose their behavior. But when the temperature is less than critical temperature, it cannot pass from the superconducting type 1. And here is superconducting type 2, including niobium, tritine, magnesium diboride. That here you can see after the BC1, just part of the magnetic vortex can pass through the superconducting, while in compared to superconducting type 1, after when the temperature is up to the critical temperature, the superconducting type 2 completely lose this behavior. Nowadays, thin film scientists suggested A15 materials for coating of the cavities. A15 materials, mainly the structure are A3B structure, like something like niobium tritine. And you can see here that the critical temperature is 18 K. And also another type of coating is B1 compound. That the advantage of this one is less sensitive to radiation damage and crystalline disorder. Something like niobium, titanium, nitride. But nowadays, the important thing is superconducting coating is magnesium diboride. That you can see here that the critical temperature of this one is 39. When CERN used 39 material, they can save lots of energy for the cooling of this cavity. And here we, our previous work that we have done in collaboration with Daresbury and Manchester University, we make niobium surface. We have done PO, plasma electrolytic oxidation, the surface, and incorporated magnesium diboride in this porous structure of this coating. And we have done all the measurements, and we get a good result of this with this technique. Oh. This one is the cavity that we have got from Atomic Energy of Italy, and the specification of this kind of cavities, substrate heating is 680, and now there was 140 layer of the niobium on the surface. But the important thing is of this cavity is many years ago, CERN used copper cavity, but they found out, but they replaced this copper cavity with the niobium. What the problem is with niobium bulk cavities, that the price of the niobium cavity is about 40 times more than the copper cavity. And even the conductive properties of the copper is better than the niobium. That's why they decided to use copper cavity, but a very thin layer of the niobium in the surface. That is a copper cavity with the niobium interface. You can see here we cut this part of this cavity, and for the preparation before the deposition of the niobium cavity, they use electrochemical polishing and chemical polishing the surface. This is the groove of the making of the spinning of the cavity, but you can see even after all the treatment, the surface or the spinning process, we have see this kind of groove on the surface. And here is the cavity that applied chemical polishing, and here is the first they're using abrasive particle and then decreasing in a surfactant solution that made by CERN and using deionized water and electro polish in phosphoric acid and butanol solution, and chemical polish in a sulfamic acid, hydrogen peroxide, and ammonium citrate in the M-butanol solution. And at the last, they passivate with sulfamic solution and read with high pressure ultra pure water. This is the cavity here. We look at the defect in two different ways. First with the CT and then with SEM, PFIB SEM. You can see we cut the cavity here, and it's in the size of 4 to 2 millimeter. And we put the sample here, and the sample size is 4 to 2 millimeter. The number of projection 2001, and voxel size is 1.89. And you can see here the defect that appear in the surface, but by X-ray tomography. And we look at all the surface, 2,000 slides on the surface, but you can see here the 3 different defects in the surface that we got from the X-ray CT. But the most important thing for X-ray CT is the resolution of the device, because sometimes when the size of the defects is less, we cannot see by CT. And here is the depression of the defect on the surface, at the same time, the same depression in the interface. And here is a 3D view of the interface of the sample. And here you can see in the surface has the same thing in the interface. It's very important for the CERN, because they would have thought that they only appear in the surface and it's not related to interface at all. And here is the result of the CT. At the same time, we look at that particle with SCM, and we see this kind of defect or crack in the surface. And we have done focus ion beam and make a strip of the plating in the surface to protect the sample. But the thickness of this niobium coating is about 40 micron. That one, it's a bit difficult for focus ion beam to reach to the interface. However, we saw this kind of defect in the interface. And again, we look at we brought the plasma focus ion beam also to bring out this part out of the sample and make EDS of this defect. And here is again focus ion beam on the grid to get the EDS result. And here you can see the EDS map in the surface, and a defect exactly located in the interface. Obviously, you can see here in EDS map. And it's the coating of niobium, and this one is the copper substrate. And this slide shows, again, EDS map, EDS of SCM result. But you can see here exactly in the interface that the niobium filled in the substrate in this part of defect. What summary of this investigation? We correlate the cavity defects, but two ways. One of them focus ion beam and also CT. For CERN was so important to, without any changes on the cavity, we can look at the defects in the surface, because it's very important to measure the performance of the cavity. And also they have to look at the spinning process, because and before and after the chemical polishing and electrochemical polishing, they have to be more careful to make sure that all the growth on the surface would remove. And we published this study in material chemistry and physics. However, lots of work left, because we don't know the relation of this, the number of the defects with the performance of the cavity. That's why in the future we have planned with CERN to collaborate to measure the performance of the cavities. And at the end, I acknowledge the European Union and INFN.
Sepidah, thank you very much. That was a fascinating talk. Are there any questions for Sepidah? Stuart, the roving mic.
Yes, hello, thank you very much. How is the niobium deposited? It's not clear.
With PVD.
As a PVD, okay.
Technique in Darsberry lab.
Right, because it doesn't have the characteristic growth patterns of a PVD deposit.
Yes, we didn't put that one here, because just in this part, INFN was in charge of the deposition of the cavity, and Darsberry was the responsibility was the characterization of that one.
Okay.
That's why I didn't put anything about the deposition of the niobium in the surface. However, we did that one in the Darsberry. Yeah.
Okay. It's just curious about how those defects arose.
Yeah.
You think it's contamination, or do you think it's a part of the growth process,
yeah.
the deposition?
It's just very preliminary work, but we found out that during the chemical polishing, we can see an enrichment of the impurities behind the crack also. That's why we measure that impurities in different way. But at the moment, we are not 100% sure that if this impurity caused the defect, but we need more work on these issues.
Okay, thank you.
Any further questions for Sepidah? So Sepidah, you talked about the magnesium diboride. I was wondering about the mechanical properties of these different layers. They're presumably very different, are they?
We measured the superconductivity in ICIS in the diamond, but we didn't use. Just I've done scratch measurement.
Right.
But at the same time, Jefferson Lab had deposited. Jefferson Lab in US deposited magnesium diboride in the surface, but after 1 month, magnesium diboride that absorbed the humidity, the blistering appear in the surface. But with PO coating, with incorporation of this one, after a few months, we have repeated all the tests, including XRD and scratch measurement. We didn't have any blistering or even any, because magnesium diboride decompose and magnesium hydroxide appear possibly in the surface. Even after the XRD, after 2 or 3 months, we didn't get any magnesium hydroxide on the surface.
Because I mean that certainly seems a promising material, just because, as you said, its temperature.
Yes,
is so
it's
attractive.
39 degrees.